So now we've talked about metathesis reactions or double replacement. Now we want to talk about another kind of reaction that takes place in solution, and these are oxidation reduction reactions. And when we talk about this, we say that oxidation reduction, or redox as we call it, are electron transfer reactions. In double replacement, we had chunks that were ions, and they traded partners at the dance. In redox, you don't have chunks of atoms trading partners. You have electrons moving around. So redox reactions are electron transfer reactions. And we define oxidation and reduction by the direction in which the electrons are moving. And we also can decide if something has been oxidized or reduced by looking at the oxidation number. So when we have oxidation, it's a loss of electrons, and we have reduction, it's gain of electrons. So I brought my friend to show you and help you remember. Can you see what he is here? For those people at home, he's a lion. So when you look at my friend, what's his name? If he's a lion, what's his name? Leo, right? Yeah, for a while, I had students for a while that would say Simba, but Simba won't help you learn redox. His name is Leo, and when I talk to Leo, hey, Leo, what's going on here? He only says one thing to me. He says, grrr. So Leo, the lion, says grrr. And loss of electrons is oxidation. The gain of electrons is reduction. So Leo helps me remember about oxidation and reduction, which way it goes. And there's not going to be a question on the test that says what is oxidation or what is reduction, but it might be a question that says what happens in the oxidation half or the reduction half of this, it's kind of top heavy there, of this reaction. There we go. So I think that can be really helpful. Now, when we talk about oxidation and reduction, we also define the oxidizing agent and the reducing agent. The oxidizing agent allows something else to become oxidized. So in order for something else to be oxidized, the oxidizing agent gets reduced. And the reducing agent allows something else to get oxidized. The reducing agent allows something else to get reduced, so it gets oxidized. And when you think about this, if you go to Hollywood to become a star, you hire an agent. The agent doesn't become a star, the agent makes you a star. So the agent lets something else get oxidized. The agent lets something else get reduced. When you think about this, there's a lot of redox chemistry going on in your house. Most people are familiar with bleach, chlorine bleach that we use to clean things maybe in the kitchen, and we use it in the laundry room. But how many of you ever read the warning label on the bleach bottle? What does it say? Do not drink, yeah, for sure. It also says, danger, oxidizer. Because bleach has the capacity to support combustion and to oxidize other things, and it can react really violently. Most people take the bleach bottle and stash it somewhere in the laundry room. I know at my house, the hot water heater is not too far away from my washer and dryer. And you have to be careful not to put that bleach bottle near the hot water heater because there is an open flame in some hot water heaters, and that can cause a serious fire or explosion. We used to have a pool in our backyard. We got rid of it. And we would go out there in the summer, and we had these big pucks, big chunks of hypochlorite that we would put in the pool to keep the bacteria and the algae from growing in the pool. And the first time we put that up, we had a little shed, And we keep the mowers and the gasoline for mowing in the shed. And Bob decided he was going to store the pool chemicals in the shed. So he took this big box of calcium hypochlorite and put it in the shed right next to the mowers and the gasoline, shut the doors, the creaky old hinges, and it gets really hot in there. And I said to him, don't do that. Why not? I said, because that chlorine tablets, those are oxidizers, and that can cause a problem in the shed. It can start a fire. It can make a fire get bigger. It doesn't start the fire. And he's like, oh, whatever, it'll be fine. Well, he's not a chemist. And so I took the chlorine and I went and put it in the garage. It was further to take it to the pool. He's like, well, what'd you do that for? 2 days later, I find it back in there. And I said, I told you not to do that. And some of you aren't married, but you probably know of marital disputes. I'm like, I told you not to do that. He's like, you're not my boss. No, I'm not your boss, but I'm the one that's going to benefit on your life insurance when you burn yourself to death by doing this because you're being stupid about storing chemicals together. So to show him, to help him understand, and our children also, I went out and built a fire in the backyard, just got some sticks and things, a small fire. I took a hammer, broke up one of those tablets, and I stood about 10 feet away and started throwing these little chunks of the hypochlorite into the fire. It's a solid calcium hypochlorite. And everybody was amazed, except me. I knew what was going to happen. Because when you throw those little chunks, they were maybe the size of a pea or so, it would just make the fire flare up. And, of course, my son, adolescent boys, got to love him. He's like, can I do that? Sure, you can do this while we're standing here, and don't you ever do this again on your own. Andrew Peck really couldn't be trusted with chemistry experiments. He got in a lot of trouble for that at school. And the sad part was that he was doing the chemistry right. But you should not take things that explode on a school bus and set them off. I did try to explain that to him. Yes, he was suspended from the school bus. He didn't get suspended from school, but he did get kicked off the bus for 7 days, and he understood later that was a bad idea because we made him walk. Okay. He's like, well, you'll drive me. I'm like, not going to happen. Because the timing wasn't right. I had to be here before he had to leave for school. But anyway, so that oxidizer stuff, it really is important. It supports combustion. So now that's the definitions. The other thing is the oxidation number. Oxidation numbers are apparent charges. They are not real. And they are sort of explaining what the charge would be if the electrons were transferred completely, which they're not. So when we think of these transfer reactions, there's a lot of different kinds of electron transfer reactions, and we'll talk about some of those types and groups, but first we're going to look at oxidation numbers. So when we're assigning oxidation numbers, we have to follow these rules, and we have to follow them in order because a higher rule can override a lower rule. So as we look at this, any element in its natural state has an oxidation number of 0. The sum of all oxidation numbers has to equal the charge on the species. If it's a neutral compound, it's 0. If it's an ion we're talking about, it's the charge on the ion. Fluorine is always -1 always. That means that fluorine has one more electron than it started with. Monoatomic ions have the oxidation number equal to the charge on the ion. If it has undergone electron transfer and it really has lost an electron, then it's going to appear that it has lost one. It's kind of like a formal charge, that apparent charge thing, but they're a little bit different than formal charge. Hydrogen is usually a +1 unless it's a metal hydride, then it's a -1. Metal hydrides are where you have something like sodium hydride, and the hydrogen is actually a -1 ion now instead of a +1. Remember, sometimes hydrogen can act like a halogen. Oxygen is a -2 most of the time unless it is a peroxide, and if it's a peroxide, it's a -1.